All right, folks, are you ready for the fun part? Here is where we take everything we've learned in the past several modules and we stitch it all together into this process called hypothesis testing, which again serves this essential purpose in research of telling us whether the data we gain from a study tells us enough to conclude that something meaningful has happened with regard to our predictions, our hypotheses. So, we're going to start relatively slowly with some big picture ideas, and then we're going to start to jump into the process of research, or excuse me, of hypothesis testing in research. Again, as I've said before, the entire rest of the semester is basically going to be variations on the framework we're going to learn over the next few videos. So watch them, rewatch them, make sure that you've got it as close to down as you possibly can as soon as possible, because this is the single most important framework and process that we have in the entire course. All right, everybody buckled up. Let's start with some basics. Remember the term inferential statistics? We talked about that way back in, I believe, Module 2. And inferential statistics involve taking information from a sample, things that we actually have measured. And remember, we have descriptive statistics to describe that. We take that sample information and its descriptive statistics, and we use it to draw inferences about a population. So we draw advanced conclusions about a data set by going beyond the data we've actually got and drawing conclusions that shape our understanding of those vast groups of people that we didn't measure, the population overall. So the inferential stats approach we use, do the patterns that we see in a sample appear to reflect those in a population? So in an experiment or in a quasi-experiment, the key question we're asking is, do differences in DV scores represent a real change caused by the independent variable, the IV, or not? As we mentioned, the big problem, they are almost always going to be at least a little bit different. We need a framework for determining which differences mean something and which ones we just can, again, kind of shrug at. So these conclusions are based on probability. Basically, we calculate the probability we'd get the results we did due to a fluke, due to just random chance or noise in the data. If that probability is low enough, we conclude something meaningful or statistically significant has happened. However, again, that probability, however low it can never, ever be zero. And that's crucial. That means that you are never 100% certain in your results. So that's one of the reasons why we avoid the word proof. That's one of the reasons why uncertainty is baked into the process of hypothesis testing. And it makes total sense. You are trying to draw conclusions about large numbers of people that you've never met, that you've never interacted with. It makes sense that you would want to be very cautious and very conservative about how you apply that. So understanding uncertainty is key to understanding the idea of inferential statistics. Our inferential stats are divided up into two different categories, parametric and non-parametric statistics. So first, 90% of what we will be doing, 90 to 100% of what we will be doing is what's called a parametric statistical test. So this is basically what we're going to be working with. Parametric statistics involve population parameters. So again, remember, parameters are those key characteristics of populations. The one we've seen a bunch of is mu, the population mean. You'll see in hypotheses for parametric stats tests, you'll see those mu's, those population parameters showing up all the time. To run a parametric statistical test, you have to make a couple of assumptions about the population of scores that you're looking at. One is that it is normally distributed. Remember, this is a pretty safe assumption. If you remember, we talked last module about the fact that if you gather enough scores on a variable, the sampling distribution always becomes normal, even if the original raw score distribution was not. So this is a safe assumption to make, but it's an assumption that we have to make. And that the variable is at least an interval scale or a ratio scale. If you remember those scales way back again from Module 2, we mentioned that your DVs, the variable you're actually measuring, needs to at least be an interval scale. Again, we always assume this to be the case in psychology. Even when we can't guarantee we have a true interval variable or that we definitely have a normal distribution, parametric statistics are still useful. They are what are called robust statistics, which means that they tend to be fairly accurate even if those assumptions aren't necessarily true. So they hold up pretty well even when those assumptions aren't accurate. Now, there are some fringe cases where you might be dealing with a population of scores that isn't even close to normal. Or, more commonly, your dependent variable is maybe something nominal or something ordinal. In that case, we can't really meaningfully talk about population means because, again, we lose that ability to order the responses from highest to lowest or to know how far apart they are. In that case, we have to use a special family of statistics called non-parametric statistics. Those stats do not revolve around hypotheses about the parameters of populations like the mean. So we don't have to make those assumptions. So let me give you an example. Let's say that our dependent variable, or variable that we're measuring, is a morbid one, but one worth knowing about, the number of people in fatal traffic accidents. Let's say, okay, we look at the numbers, and across America, about 18 in 100,000 people have a fatal traffic accident annually. In Arkansas, the rate is a bit higher. It's 23 in 100,000. By the way, these are old scores. I have no idea if they're true now, but for our purposes, they're true. So is that big enough to say that there's a meaningful difference there? That driving in Arkansas overall is more dangerous than driving in the rest of America? And the number's higher, but you'd expect a little bit of fluctuation. Some states will be a little above or a little below average just due to just pure chance. It's just the way numbers work. It's very unlikely you'll get exactly the average. So is that difference of 5 people out of every 100,000 a meaningful difference? Again, that is a nominal variable. It's a yes, no. You either were in a fatal traffic accident or you weren't. So it's a dichotomous nominal variable. We would need some kind of non-parametric stat to test that. However, what we will be doing with our parametric statistics, we will be learning a framework called null hypothesis significance testing. You'll see this marked as NHST sometimes, or generically I just call it hypothesis testing. It's all the same thing. It's a process for figuring out if you can draw conclusions about your population based on your sample, if the things you see in your sample support predictions you make about your population. The key factor here, the key thing that we look at, as we talked about in the last module, is probability. Probability that you could see results like these due to chance. If your results are very unlikely, it's unlikely you'd see them due to chance, you conclude that the populations that your hypotheses regard probably do actually differ. Probably, but not definitely. There's that idea of uncertainty again. So maybe I randomly assign people to take a drug, an antidepressant, and other people take a placebo. I measure changes in their depression. I need to figure out what's the likelihood of seeing a difference as big as I do if I do see a difference in those conditions. What's the likelihood of seeing a difference this big if there was really nothing happening, if the drug wasn't any different from a placebo? The lower that probability is, the more confidence I have. I could do the same thing with the effects of violent media consumption on anger, with the effects of social presence, people observing you, on productivity at work. Again, I would be comparing these different conditions on their DV scores, and I need to figure out what's the likelihood that I would observe the differences I do purely due to chance. So that's null hypothesis significance testing. We're going to spend the next couple of videos kind of unpacking how this works, and then again we're going to be practicing it several times over and continuing to use this framework in just about every other module from here on out. So unsurprisingly, it's the most frequently used inferential stats technique there is. Certainly not the only one, but it's definitely the most common one and the most commonly taught. Here's how null hypothesis significance testing works very generally, and then we'll get into some specific aspects in the later videos. We start by generating hypotheses. As this is a parametric test, they involve population parameters, specifically the population means. Basically, we are making predictions about whether the means of 2 different populations, the one we're actually concerned with and our basis of comparison, the people we're going to contrast them against, we make predictions about whether they're equal or different, and sometimes in what direction they might be different. So let's set up an example, and then we're going to take a break. We'll come back in the next videos and explore this example as we kind of put together this framework. So let's say Doritos, they make a lot of chips. Let's say they say that a certain size bag of chips will contain 185 grams of chips on average. Okay, so if you're a big Doritos eater, maybe you think, oh, they're not really giving you that much. Sometimes I open it up and there's not much in there. They say, oh, it always weighs the same. It's just settling. You say, I don't know. Maybe you're trying to put one over on me. We could use hypothesis testing, null hypothesis significance testing, to assess this. Basically, what Doritos has done is they've made a statement about a parameter, a population mean. They said the mean amount of chips in these bags is 185 grams. That's something that we could test. We could falsify it. We could find evidence that that is not the case, or we could find evidence that perhaps is more supportive of that. What we would want to do in this test is say, okay, there's a true population mean out there, the real actual average amount of chips in all of the Doritos bags on Earth. That's the real population mean. We're going to call that mu1. We're going to gather information using a sample, because we can't measure every single Doritos bag, that's going to represent mu1, and we're going to compare it to what they say the population mean is, 185. So what we're trying to test, and again what we're going to learn how to test, is has Doritos made a reasonably accurate claim, and how do we know? To determine it, we're going to need to start by developing hypotheses about those population parameters, and that's what we're going to do next time. I will see you there.